Okay, this is the sixth and last video for the completely randomized design portion of chapter 11. We are about to reproduce Levene's test for homogeneity of variance, which normally precedes one-way ANOVA. But in this chapter, they wanted to show ANOVA first. The reason for that is probably the fact that in Levene's test for homogeneity of variance, ANOVA itself is also used, but not with means, but with the differences from median to the individual values. Before they introduce Levene's test for homogeneity of variance, they list ANOVA assumptions, which are also given, usually, before running the ANOVA test itself. But this chapter is a little unusual because they had their reasons to present it at this moment. So let's go over them pretty quickly and then get straight to Levene's test. It's right over here. It's number 3. In chapters 9 and 10, you learned about assumptions made in the application of each hypothesis, testing procedure, and the consequences of departures from these assumptions. To use the one-way ANOVA F-test, and once again F-test has to do with the ratios between variances, you must also make certain assumptions about the data. These assumptions are randomness and independence, normality, and, this is what we are after, homogeneity of variance. The first assumption, randomness and independence, is critically important. The validity of any experiment depends on random sampling and/or the randomization process. To avoid biases in the outcomes, so far this should be understood pretty easily. We want to make sure our measurements are independent so they don't influence the data unduly, and randomness meaning giving each data point an equal chance of being part of the measurement. To avoid biases in the outcomes, you need to select random samples from the C groups or randomly assign the items to the C levels of the factor. That's the key word here, factor. We have 4 groups here because we have 4 suppliers, 4 groups of 1 factor, which is the supplier. Or as they put it, which supplier to choose. They put it in the form of a question. The factor in this part of the chapter, which is ANOVA, the factor is the supplier. Selecting a random sample or randomly assigning the levels ensures that a value from one group is independent of any other value in the experiment. Departures from this, the experiment here consisted obviously of taking measurements of tensile strength, but part of the design of the experiment was grouping the parachutes so that the suppliers could be chosen according to the group. And in this part of the chapter, nothing was said about the looms on which these parachutes were made. So we are pretending we're dealing with identical equipment on which 4 different fiber types, the fibers from 4 different suppliers, were used to make parachutes. Selecting a random sample or randomly assigning the levels ensures that a value from one group is independent of any other value in the experiment. So we made sure that the parachutes did not mix. The suppliers did not mix. We grouped them according to their suppliers. Departures from this assumption can seriously affect inferences from the ANOVA. These problems are discussed more thoroughly in references 5 and 8. The second assumption, normality, states that the sample values in each group, again we have 4 groups, are from a normally distributed population. Normally distributed population, that has to do with the distribution. We only have 5 measurements in each group. Just in the case of the t-test, just as in the case of the t-test, the one-way ANOVA f-test is fairly robust against departures from the normal distribution. Robust test means it detects the departures from normality. In other words, if your measurements are very weird, you'll fail the test. As long as the distributions are not extremely different from a normal distribution, the level of significance of the ANOVA f-test is usually not greatly affected, particularly for large samples. The level of significance is our assurance that the measured value was not obtained by chance. So we look at that value before and after the critical value. Anyway, this is something that people need to be reminded all the time. What level of significance means. You can assess the normality of each of the C samples, we have 4, by constructing a normal probability plot or a box and whisker plot. Okay, this is easier done in SPSS. We're not going to do that. The third assumption, here it comes. The third assumption, homogeneity of variance, states the variances of the phi groups are equal. We have 4 here. If you have equal sample sizes in each group, which we do, we have 5 samples in each of the 4 groups. Inferences based on the F distribution are not seriously affected by unequal variances. So even if the variances are unequal, the inferences will not be greatly affected by that inequality if the sample sizes are equal. However, if you have unequal sample sizes, unequal variances can have a serious effect on inferences developed from the ANOVA procedure. Thus, when possible, you should have equal sample sizes in all groups. We do. The Levene test for homogeneity of variance presented on page 432 is one method, it's a method, to test whether the variances of the C groups are equal. When only the normality assumption is violated, the Kruskal-Wallis rank test, a non-parametric procedure discussed in section 12.6, is appropriate. When only the homogeneity of variance assumption is violated, procedures similar to those used in the separate variance t-test of section 10.1 are available. Most likely that's reading of the results of test according to the assumption when the homogeneity of variances is assumed. That's one line in the table. When the homogeneity of variance is not assumed, that is when we fail the test, that's the bottom line in the table. When both the normality and homogeneity of variance assumption have been violated, assumptions, you need to use an appropriate data transformation that both normalizes the data and reduces the differences in variances. See reference 9. Or use a more general non-parametric procedure. See reference 2 and 3. We're not going to do it right now. Finally, here comes the Levene test. Although the one-way ANOVA f-test is relatively robust with respect to the assumption of equal group variances, large differences in the group variances can seriously affect the level of significance and the power of the f-test. We're not discussing power of the test here right now, but it's good that they mentioned it because it's something we'll look at later. The power of the test. One procedure with high statistical power is the modified Levene test. This is what they'll be using in Excel, something they call the modified Levene test. The Levene test performed by SPSS, for example, does not use the word modified. its test statistic will look a little different. And they used Levene statistic for that test, not the F statistic. Okay, to test for homogeneity of variance, he used the following null hypothesis. This is the answer to the question, what is the null hypothesis in the Levene's test for homogeneity of variance? And the null hypothesis is obviously the equality of the variances. Sigma is standard deviation, sigma squared is the variance. And we're using the Greek letters because we are making inferences for the entire population. And one more reminder, in this chapter the groups are the populations. So we're testing this null hypothesis against the alternative that not all variances are equal. There could be differences. To test the null hypothesis of equal variances, you first compute the absolute value of the difference between each value and the median of the group. So the Levene test deals with the medians. We're going to use the Excel command for that. We were going to use, but actually the medians had been calculated before the book shipped to us. They came in a data file. We already have medians there. When you perform a one-way ANOVA on these absolute differences, absolute means these straight brackets, they show that we're going to just drop the minus sign. To illustrate the modified Levene test, once again, this is the modified Levene test. Return to using statistics scenario that's in the beginning of the chapter. We're going to reproduce this table, and from these values we'll run the one-way ANOVA, which will reproduce this table over here. So these are the medians. Next step is to calculate the absolute differences between the medians and the individual measurements. We're going to do it by using the ABS function in Excel. We'll have to copy these headings, the column headings, because we'll need the analysis of variance to be, for the Levene test, to be appropriately labeled. So we have, this should be C. G, and E. Okay, we'll do it for our 5 measurements and copy the column headings. Okay, I'm going to save this. Now 0, 5.5, 1.3, 1.4, 0.05. Do we have it? Yes, 1.8, 2.3, 2.2. Yes, we've got the correct table. Now, based on these values, we're going to run the ANOVA. As we've done before, we're going to data analysis, single factor ANOVA, we get our range, and yes, we have labels in the first row. We'll pick the output range right here, so we don't have to look on the other tab, and fire it up. Okay, so just by looking at p-value, we do not reject the null. Let's compare it with the text. We have just reproduced this table, and now we have 0.89 p-value, correct? That's correct. 3.2 critical value for F statistic, and 0.2 for F. Okay, this is done. The conclusion here from figure 11.8, which is this, or as we have it in a clear version here. The F calculated is less than F critical, and as I mentioned, just by looking at the p-value, we do not reject the null, and the null was the variances are equal. Thus, you do not reject the null. Do not reject the null. There is no evidence, this is how you write the conclusion, there is no evidence of a significant difference among the four variances. In other words, it is reasonable to assume that the materials from the four suppliers produce parachutes with an equal amount of variability. Okay. We established the variability, equality of variability. Therefore, the homogeneity of variance assumption for the ANOVA procedure is justified. And normally we would have proceeded to run the ANOVA on the means, but we did that before. Here's the example they give us. Fast food restaurants and drive-through times. The average numbers for drive-through service. 150 for Wendy's, 167 for McDonald's, 169 for Checkers, 71 for Burger King, and 172 for Long John Silver's. Okay, let's put this in a neat little table like that. These are the values for the means. And this is the reproduction of the table which they show us. They pretend they've already run the ANOVA for the means. Here's the question they want us to answer. At the 5% level of significance, is there evidence? Now, this question will pop up on many problems, including the ones on the test. Is there any evidence of a difference? And they're dropping a word here, they're missing the word significant difference in the mean drive-through times of the 5 chains. In other words, they're telling us to look for differences which are not negligible. This is pairwise comparison, for which they tell us, well, we're going to have to use the Tukey-Kramer procedure. That's the multiple comparison procedure that this chapter uses. So first, we need to state the hypothesis that concerns the means. And this is the ANOVA for the means, that the means are equal. The alternative is not all means are equal. I'm telling them this could be not equal, or maybe all of them maybe not equal. Then we state the decision rule. Because we are given the level of significance of 5%, if p-value is less than 5%, that means the point will land in the rejection zone. Reject the null. Now, they write because the p-value is virtually 0 right here, which is less than 5%. Reject the null. Obviously, this is behind, this is in the rejection region. You have sufficient evidence to conclude that the mean drive-through times of the 5 chains are not all equal. But this is not what we're looking for, right? They ask for difference. Now we need to calculate the differences to determine which of the means are significantly different from one another. Significantly is the key word. Statistically significant. Something we cannot overlook. Use the Tukey-Kramer procedure, which we used before. We have the formula to determine a critical range. But before doing that, we have to go to the studentized range table and get ourselves the critical number before plugging it into the formula. Now, in this calculation, C remains at its original level. This is the 4 groups. And now here this is 5 groups. These are not parachutes anymore. We have 5 chains. And they also told us that the study was based on 20 customers for each fast food chain. 20 customers for 5 chains. That will give us 100 for the N. This N is 100 because we have 5 chains from which 20 customers were sampled. And 100 minus 5 will give us the 95. This can be looked up on the internet. We already looked this one up in the table on page 810. Now let's do something different and go to the internet and get it from there. And let's not forget we have 5% significance level here. Here's the 5% table I just looked up. And in it, we remember about the degrees of freedom in the numerator, that is 5, and in the denominator we had 95. The closest to 95 here will be 120. We're past 80, not there yet, not at 120, but that's the closest in the table. So we use this, we'll round it off to 3.92. That's how we did it this time. We got the studentized range value from the internet, not from page 810. We plug it here, and we get the critical range calculated by hand. Okay. Again, the reminder is that we have 5 chains here. Now, to run the Tukey-Kramer procedure in Excel, we're going to have to use what they supplied us with, the authors. This file, Tukey-Kramer file, which has the layouts for 3 groups, 4 groups, and obviously we're going to use the layout for 5 groups. We're going to copy this and use it here. Okay. We have sample means that we just copied, I just copied from the previous sheet. Okay. We're going to get our means. And we remember the sample size was 20 for each restaurant. Denominator degrees of freedom. Okay, the numerator obviously was 5 by default because that was the tab. Tukey-Kramer for 5. Denominator degrees of freedom, as we remember, was 95. Now the mean variances, mean squares between within groups had to be calculated from the table they gave us. Let's just copy it. And the Q statistic we just looked up on the internet which turned out to be the same as what they used here. 3.92 was 3.197. We'll use 3.92. And we've got 4 substantial differences, significant differences. 1 to 2, Wendy's and McDonald's. 1 to 3, 1 to 4, and 1 to 5. Obviously, this beats everything, which we could have told anyway. But to assign statistical significance to our conclusion, we had to run the Tukey-Kramer procedure. And this is how they concluded. Any observed difference, they misspelled it, should be difference, greater than 10.02 is considered significant. The mean drive-through times are different between Wendy's, whose mean is 150 seconds, and each of the other 4 chains. Here's the statement. With 95% confidence, you can conclude that the mean drive-through time for Wendy's is faster than McDonald's, Burger King, Checkers, and Long John Silver's. But the mean drive-through times for McDonald's, Burger King, Checkers, and Long John Silver's are not statistically different. So in this particular exercise, their differences are negligible. This concludes the completely randomized portion of Chapter 11.